When I first picked up this paper about gray foxes, I honestly didn't expect it to change the way I think about genetics. But it did. The article published in Cell in September 2025 is called Reference Genome Selection Impacts Results of Population Genetic Studies. It explores how just picking the wrong reference genome, like using a dog genome to study fox DNA, can twist our entire understanding of variation and evolution. And the best part, it connects directly to what we learned in week 7 and 8, genetic variation, Hardy-Wilburn equilibrium, and drift. Let me show you how. So here's the key finding. When researchers mapped gray fox DNA to his own reference genome, they detected around 25 to 33% more SNPs than when they used a dog or Arctic fox reference. They also uncovered about a third more rare variants, those low frequency alleles that tell us how genetically diverse a population really is. That immediately reminded me of week 7, where we measured genetic variation using heterozygosity and polymorphism. Those values depend on what alleles we actually detect. Think of our A1ATD exercise, where we calculated allele frequencies and heterozygosity using the T allele frequency of 0.1225. If the sequence's reference missed 30% of those alleles, our results would be completely off. We'd underestimate diversity, even if underestimate disease risk. What this paper really says is, even perfect formulas can give us wrong answers if the underlying data are incomplete. And the completeness depends on the reference genome. But the impact doesn't stop there. The authors discovered that using a mismatched reference skews evolutionary inference, things like effective population size and selection signals. That's exactly what we explored in week 8. Hardy-Wilburn equilibrium gave us a null model. But the article warns that if the site frequency spectrum is biased by a bad reference, our Hardy-Wilburn tests start lying to us. Remember our cystic fibrosis problem? We need Q2 equals 1 over 2,700 to get Q equals to 0.019. If a bad reference caused us to miss rare alleles, Q2 might look like 1 over 3,000 given Q equals to 0.018. That small difference might push us to think the population is or isn't in equilibrium, completely changing the conclusion. The same applies to drift. In our week 8 model, heterozygosity dropped from 0.5 to 0.167 after 6 generations. But if reference bias already has diversity, we could wrongly assume drift is stronger than it really is, a serious issue in conservation studies. Before reading this article, I never questioned where our genetic data came from. I used to trust the numbers we analyzed, SNP counts, allele frequencies, heterozygosity were simply true. But the study made me realize there's a hidden layer beneath all of that. The reference genome silently shapes what we can even see. It's like trying to read a sentence with missing letters. The meaning changes, but you might not notice. Now, when I revisit our week 7, week 8 workshops, I think differently. For non-model species like gray foxes, using the wrong reference could make a healthy population look in danger. That's not just a technical error, that's a conservation risk.